So we're going to dive straight into empirical statistical testing. So we're actually going to start talking about specific techniques, and each technique is going to be defined by your methodology. So again, we need to know what our independent variables, our predictors are, what our dependent variables are, our outcomes. We need to know how many of each one and what type of data is each one. So again, like categorical versus continuous. Once we know that, we can start looking to see which particular statistical tool we need to use to run an analysis to actually test whether the differences or relationships that we found in our sample data is trustable. And again, that trust, that measurement of probability, is specifically looking at how likely is it that it's due to chance versus a meaningful relationship. Now again, not cause, simply a relationship. Remember that cause cannot be proven statistically. Cause has to be proven methodologically. Now, no matter what the statistical technique we're going to use from this point on is, whichever tool it is, whether it's an ANOVA, well, whether it's a multiple regression, or whether it's various more advanced techniques, or some of the simpler ones like t-tests, we're always going to run through the following stages. So this slide is actually very important. And I really want you to remember that no matter what we're doing, this slide kind of stands as the bedrock of the process of statistical testing. And stage one is to compute the descriptive statistics. And this is a stage that's often lost or not done necessarily in a lot of studies. So we really need to focus on the fact that, again, our statistics are mathematical equations. They don't know what we're putting in them. And we need to make sure that we are not violating the assumptions of that mathematical statistic. And the first thing we need to do that is to compute our descriptive statistics, especially on any continuous variables. So any continuous variables we have, especially if they are a DV or an outcome, we're going to compute descriptive statistics. That includes mean, that includes standard deviation, but that also includes some checks for assumptions. And this part of this lecture, the first third of this lecture, is really going to focus on what are we looking for with those descriptive statistics. And if there is a violation, what can we do about it? So again, we're checking the assumptions. And stage one is, from a statistical viewpoint, focused on those descriptive statistics, but this is also about checking all the assumptions, making sure that we're using the right test based on what our data looks like, again, what our IVs and DVs are. Once we know that we have the right test, it's the appropriate test to run, and we're not violating any of the assumptions of that test, now we actually compute the test. We run SPSS, or if we wish, we can hand calculate. And we're going to get an actual value from that test. Once we actually have that value, we're going to evaluate the nature of the effect. We're going to ask, is that value big enough that it passes the bar of whatever we've set as the proportion, the p-value, that we're willing to accept the chance of us being wrong. Again, in the social sciences, almost always 0.05, 5% chance of or less of being wrong. But when we compute the test in stage two, we don't get a p-value. We get an actual value based on the variance in our study. That means that's why we move to stage three. We look at that value and determine, is that value a value that would have occurred less than 5% of the time by chance alone? If that value is significant, if that value is less likely to occur due to chance than 5% of the time, we move on to stage four, which is evaluate the effect size. If significant, we calculate the effect size. So once we find a significant effect, our next step in any statistical technique is to now quantify how meaningful is that effect. And think about this as a three-stage process. Stage two is a value that is dependent on your measures. It is a value. It really doesn't tell us that much. We need to take that value and in stage three ask, how likely is it due to chance? And in stage four, we need to ask, how likely is that value, or how meaningful is that value? How big of a difference or how strong of a relationship is that value indicating? And in most cases, this requires a little bit of additional math to put that initial value that we get in stage two into some kind of effect size metric that is common across statistics. Finally, once we've actually evaluated the effect size, we're going to go to the final stage, which is 5, the interpreting the meaning of the effect. Direction of the relationship, means, standard deviation, etc. In other words, we're now going to define in terms that hopefully our readers can understand, what does all this mean? So again, anytime we run a statistical test, we're going to check the assumptions, we're going to check the descriptive statistics, we're going to calculate the test and report the value that we calculated. We're going to evaluate and find out what is the p-value and report that p-value. If that p-value is significant, 0.05 or less, we're then going to calculate and report the effect size, and we're going to end up by actually putting it kind of back into English, but also with mathematical terms, means and standard deviations. What is the difference? Which group was higher and how much higher? How strong was that correlation between the IV and the DV if they were both continuous? We need to do all 5 of these steps, and when we report data, we need to effectively report all 5 steps. So let's talk about those descriptive statistics. Beyond mean and standard deviation of a continuous variable, we also want to look at the distribution itself. And we can do this by eyeballing it and actually create a scatter graph of the data. But what we're really interested in is whether or not we're violating statistical assumptions. And the first statistical assumption that we need to check is skewness. And the equation for calculating skewness is shown right there to the right. And you can see what we're going to be doing is we're going to be taking the actual individual score minus the mean brought to the 3rd power. We're going to do that for the square root of n number of participants we have. Then we're going to divide that by the sum of the number of participants we have. Again, individual scores minus y squared, or the mean. Again, multiplied, this time actually brought to the 2nd power, but the entire value brought to 3 to the 2nd power. Actually, we're not going to calculate that. SPSS does it for us, and this is one of the times we're going to go, you know, that's good enough for us. So we're going to be using the SPSS readout. We're simply going to click when we go through SPSS on any descriptive statistics of values that we're looking at in a statistical test and ask for it to calculate skewness. Now, it's going to give us a fair amount of information, and there's still a little bit we have to do with this numbers. There's some simple math we have to do. We have to do a multiplication. And what we need to do is, these are the 2 numbers we really want to look at, because the first one is the statistic itself. This is whatever the variable we're looking at. So let's say this was an outcome variable. We were looking at number of snack cakes eaten on a ratio scale. And what we find is that the skewness statistic is a negative 0.364. Now, that isn't enough to tell us if it's skewed or not. So just because it's positive or negative and it isn't 0 doesn't mean it's skewed and violating the assumption. Now, it is probably skewed. The only time we have data that's truly absolutely not skewed is if the statistic is 0. And that is extremely rare in real-world data. And our tests are fairly robust, which means they're resistant to skewness. But there's a certain breaking point where we can't trust the results anymore. And that's where we get the standard error of the skewness, in this case 0.172. Now this is where we have to do that little bit of math. We need to multiply that number by 2. In other words, we need to multiply it by 2. There's no really easy other way to say that. So again, what we're looking at is if the skewness statistic is greater than 2 times the standard error, it's positively skewed. If the skewness statistic is less than negative 2 times the SES, the standard error of the skewness, then it's negatively skewed. So in this case, we multiply 0.172 by 2, we get 0.344, which tells us that if our skewness statistic is above positive 0.344, it's positively skewed, and if it's below negative 0.344, it's negatively skewed. Now let's go back to that statistic. It's 0.364 negative. It is less. So negative 0.364 is less than negative 0.344. And in this case, this is negatively skewed data. We couldn't use this data in most of our statistical techniques. It has violated the assumption. It's too skewed for us to trust any results if we put this value into our statistical technique. Let's say we were doing a correlation. Now, the reason we have to test this is if I ran that correlation, I might still get statistical values. I might still get information. I might get statistical significance. Because again, the correlation is just a math equation. It doesn't know whether or not the data that we're putting in it is appropriate for the math equation it's doing and for the estimates of probability that it's going to conduct. That's why we have to do this process first. So after skewness, we're going to check for kurtosis. So kurtosis is the shape of the distribution, whether it's very narrow versus very wide. So this is again where we get to that concept Mesokurtic is normally distributed, platykurtic is flat and wide distributed, and leptokurtic is very narrowly distributed. And again, there's a fairly large equation, even a little more complex than the last one, to calculate the actual kurtosis of any set of data. But again, SPSS gives it to us in the same format, and we're going to be looking at it in the exact same way. In this case, we're going to look at the kurtosis box. And again, we're going to get a statistic, and we're going to get a standard error, and we're going to do the exact same thing. We're going to multiply the standard error of the kurtosis by 2. Technically by -2 and +2, but again, we're creating a range. And again, if our statistic falls within that range, that means that we have normal distribution, or normal enough for us to be able to trust it in our equations. So in this case, the standard error is 0.34. We multiply that by 2 and basically find that as long as our kurtosis statistic is between -0.684 through 0 and on to +0.684, we have a normal distribution. In this case, our statistic is -1.4, very much within that range, and therefore we are normally distributed. It's mesokurtic. We could use this in further analysis. Now, the other thing we want to look at in normal distributions, one of the first things, once we find that we have violated either skewness or kurtosis, more often than not, this is going to be for skewness. One of the things we can look at is a simple fix of, do we have outliers? Outliers are usually participants that are 3 or more standard deviations away from the mean. So let me make it clear, we're leaving the statistics of our calculation of skewness and kurtosis. We're not using those numbers anymore. We're going back to just the raw descriptive data of the variable that was found to be skewed. At that point, we simply want to find out what's the mean of that data and what's the skewness. So in this case, I've got an example down below. We've got a mean of 4.35, a skewness of 0.68, and a kurtosis of 1.32. So that skewness was probably skewed data. We've got some positive scores. So what we can do is we can actually look to find out what was the standard deviation of this distribution. And if we take that standard deviation and multiply it by 3 and add it or subtract it from the mean, any value that's outside of that range is a potential outlier. And that outlier potentially could simply be removed. Now, before you remove outliers, you have to ask yourself, is it appropriate to remove that outlier? And what I mean by appropriate is that if your data set was actually looking for extreme people, you probably don't want to eliminate an outlier, because they're not, an outlier is not just a statistical technique. They're more than 3 standard deviations away from the mean, which means they're very unlikely to appear in the population. In other words, if you randomly grabbed 100 people in a population, you'd have less than a 1% chance of finding an outlier in that group. Which means that if you're looking at kind of average behavior, if you by chance got 2 or 3 outliers in one data set, those are people that probably are not, they're basically making your data not represent the larger population. So you do want to methodologically and theoretically, so we're not talking statistics, we're talking about you making a choice as a researcher, is it appropriate to remove that outlier from this data set? If it is, and they are more than 3 standard deviations away from the mean, you can remove them, and a lot of times removing them will, once you recheck the data, you'll find that the skewness is no longer violated. Now, whenever you remove anything from your data set, whenever you do anything to your data set, you have to report it in your methods. Anytime you report this, whether it's a poster, whether it's a paper, whether it's a thesis, whether it's going to be published, anything you do to the data before you finally run the analysis, you do need to report. But you can report the violation of an assumption because of skewness. We looked at the data, found an outlier. The outlier really wasn't relevant to the study and therefore was removed, returning the data to normality. So again, outliers can cause violations of homogeneity of variance and normality. So the normality is what we've been talking about, normal distribution. But what if we've got an outlier in one of our 2 groups? That's a violation of homogeneity of variance. And that's why I'm saying that sometimes we'll be removing outliers in other situations. So for example, if I had 100 people in a study, randomly assigned 50 to one condition and 50 to the other, and I had one extremely high performing person, and they ended up in one of the groups, of course, randomly. But the other group did not have a high performing person that was that much above the norm. That person's now going to drag his group to the positive regardless of my manipulations. That's a violation of homogeneity. Homogeneity means sameness of the variance. In other words, one of the groups is going to look different in the variance than the other. Now, we want to find differences in means. We don't want to find differences in how the distributions look. Now, if you don't have outliers, or if it makes sense to leave the outliers in, but you're still violating your assumptions, the next thing you can do is a potential nonlinear transformation of the sample data. Now, I'm not going to go much into this. If you find yourself in this situation, this is honestly a little bit more of an art than a science. What you're basically doing is trying various mathematical techniques, for example, squaring your data, taking the square root of your data, taking your data to the third power, doing a logarithmic transformation of your data, and different types of violations sometimes respond better to these techniques, but there is no rule here. So if you find yourself in a situation where you violated kurtosis, you can't remove outliers. I would suggest, honestly, using your skills as a scientist to do some research on nonlinear transformations. Read up on it a little bit, look online, watch some YouTube videos, honestly, and figure out potentially what is the technique that's going to be best for the distribution that you have. And then try it. And if it works, you'll transform it. You'll check the normality, find that you're no longer violating kurtosis or skewness, and then you can run your analysis. But again, you do need to inform people that you've done this transformation. And if it's your outcome, remember that you are now getting an outcome in a very different set of, like if you had a 1 to 5 scale, if you take the logarithmic transformation of a 1 to 5 scale, at the end when you find significant differences with that transformation, remember that the numbers that you're getting, the means and standard deviations, are no longer on that 1 to 5 scale. So you're also going to have to do a little bit of kind of unpacking everything at the end if that's what you end up doing. So again, I just got the example from up above. So participants, 3 or more, mean of 10, standard deviation of 3. That basically means that anyone 10 minus 9 to 10 plus 9, so 1 to 19, any score within there is probably not an outlier. But anyone that had a score below 1 or above 19 is an outlier. And again, here's an example of that data at the bottom. So we have a mean of 4.35 on the original scale. And notice the original scale went from 0 to 10. We had a skewness of 0.68. It was skewed to the positive, and we needed to transform it because we didn't want to remove our outliers in this case. So we do a square root transformation. We took everyone's score and we take the square root of it. Now notice that our scale is now 1 to about 3.5, because again, it's the square root of numbers from 0 to 10. Our mean is cut in almost in half, 2.03, in fact, a little bit below half, but now our skewness and kurtosis are no longer an issue. So we can now run analysis on this data. We've not violated the assumptions, but we have changed the scale from the original scale that we used. So let's talk a little bit about hypothesis testing, and specifically how that we're testing hypotheses with these statistical techniques, these mathematical equations. So we've tested we've done stage 1. We've tested our data, we've done distributions, we've looked for violations of assumptions. Now we're going to start talking about what we do when we have to move forward to actually using a statistical technique. So again, step 1 is we state our hypothesis. And again, remember there's always an unspoken, unless it's your actual hypothesis, null hypothesis. And that null hypothesis is that your predictors, your IVs, had no effect on your outcome, your DFIs. Then we have an alternative hypothesis that our independent variables, our predictors, do affect our outcome, or DV. And all experiments assume that the null is true. So again, we go into this assuming there is not a relationship. We're looking for kind of overwhelming proof that there is. And that overwhelming proof is step 2. We state the criteria for rejecting the null hypothesis. And this is alpha, the probability of obtaining your score by pure chance. And again, we have to determine how low the alpha must be to reject the null. And the social sciences, this has pretty much been standardized, like I've been saying over and over again, at 0.05. So just a quick note, and you want to drum this into your head, alpha is always 0.05. Alpha is the standard. Alpha is the standard for rejecting the null hypothesis. P is the actual probability in your data set, and you're matching P to alpha. You want your P to be alpha or lower. And again, just a reminder that that idea of the one-tailed versus two-tailed test, when we do a two-tailed test again, our actual test statistic to reject the null hypothesis is positive or negative 1.96, which is fairly high up on that scale. It's a very small number of people because, again, it's 2.5% of the possible scores you could ever get on either side of the tail. Step 3 is obtain a random sample from your population. So we go out and we get people to test. We bring them into our study. We gather data. And step 4 is we compare that sample data to the null hypothesis and compute an inferential statistic. And again, I want to focus on the use of the word inferential here. We're inferring that our sample represents our population. Now, how we get our sample is, again, methodology. Back to step 3. Obviously, if we can, we want a random sample from our population. But remember, that's a very hard thing to do. We have to identify every single person in the population, and then we have to make sure that they have an equal chance of being sampled into our study. Most of the time, we're not going to have a random sample. We're going to have a convenience sample. But once we have that sample data, we're then going to look at, is the relationship that we find statistically in that sample strong enough, large enough, that the chances of it occurring by pure chance is 5% or less. And why we're computing that is that chance is how likely is it that we would find this over and over again if we kept testing the population. In other words, we're inferring from one sample what we would find in anyone else from that population. So we reject the null of probability if our results are less than alpha. If we find that the chances of us finding an effect and that effect being due to chance is less than 5%, we reject the null hypothesis. We support our alternative hypothesis. We say we found statistically significant results. If we fail to reject the null, that means the probability of our results is greater than alpha. So let's start talking about actual statistics. So you're going to see this graph grow, and we talked about this graph or this figure earlier in one of the other lectures, but this is basically going to start walking us through the various tools that we're going to cover in this class. And the first tool we're going to cover in this class is honestly the very simplest statistic that there is that is still an inferential statistic. And the question here is, how many variables do we have? And the answer here is, I've got one. I don't have an IV, I don't have a predictor, I have a single outcome from a single sample. Now, normally that might just be descriptive statistics. However, if I have access to information about the population already, I can compare my sample to the population and ask the question, is my sample different enough from the population that that wouldn't have occurred due to chance? And there's two techniques we can use, the t-test or z-test for single samples. And these are very similar tests. The only reason we're going to learn both is both of them have slightly different assumptions and slightly different times that you can use them, which means both of them are still relevantly useful for this particular type of design. And this really is a design where you didn't have a design. You've got one outcome, but you happen to have access to information about how the sample in general performs, or the population in general. So for example, you might be using a psychological test of stress. You give it to a class, you have everyone's stress score, but you didn't do any interventions. You aren't testing to see if anything fixed anything or not. You're just asking, how stressed is my class? But on this particular test, when you got a hold of it, the company that makes the test also provided the average score on that test. That's a known population sample at that point. You can now compare the stress levels of your class to the known average of a larger group of people who have taken this test. So we're going to look at the z-test for single samples first because it is the easiest statistic. It is also the only statistic that has a set value for actually rejecting or accepting the null hypothesis. So the z-test for single samples is based on the z-score. And just a quick reminder of what a z-score is. A z-score is simply a way to take any scale on a continuous variable and put it on a common metric. And that common metric is standard deviation units. So the concept behind a z-score is no matter how you measured your outcome, and this would be a continuous or ratio variable. It can be on a 1 to 5 scale, it can be on a 1 to 100 scale, it could be on a negative 500 to positive 500 scale. It could be on a negative 10 to a positive 300 scale. Does not matter what the scale was. It could be on Fahrenheit, it could be on Celsius, it could be units of energy, ergs. What we're going to do is once we have anyone's individual score on whatever that scale was and the mean and standard deviation of that scale of the total sample, we're going to take each person's individual score minus the mean of the whole sample divided by the standard deviation of the whole sample. What this does is create a z-score. So we're replacing the person's original score with a z-score. And the z-score puts whatever the scale was on a -3 to +3 scale. Actually, it can go over -3, it can go over +3, but remember the chances of a score being over or under -3, if it's a normal distribution, are well below 1%. It's about 1/1000th. So generally, the vast majority of scores, especially in a relatively small population or sample, is going to be between -3 and 3. If someone has a 0 score, they're at the mean. They are at the average. If they have a 2, they're 2 standard deviations above the mean. If they have a -1, they're -1 standard deviations below the mean. And we can also then use this information to determine their percentiles. How many people do they score higher than? How many people do they score lower on? And again, this is an estimate, but it's a useful tool. The z-test for single samples uses these z-scores effectively to calculate an inferential statistic. So again, 0 is the mean, +2 is 2 standard deviations above the mean, which means that only about 2.14 people or 2.16 people are above that. So you scored above about 97% of the population. Now, let's take a look at the z-test. The z-test is fairly straightforward. Is the sample mean, the mean that you got from your sample, significantly different from the population mean? Now, in this case, we do need 2 pieces of data to run this score. And those 2 pieces of data in this case are, we have to know the population mean and the population's standard deviation. We need to have the mean of our sample, and we have to have the n of our sample. So those should be easy. You captured the sample. You know how many people were in it. That's n. And you can calculate the mean of that sample. But now you have to compare it to a known value of the population. This can often come from census reports. It can come from white papers on various statistical techniques. It may simply just be that you're comparing one class to previous classes and you have 10 years of test data in the same test. And you're looking at the sum total mean and standard deviation of test scores over 10 years versus this one particular class. So what the population is simply, that's methodological again. What is the population you want to compare your sample to? But once you've determined that population, you have to have access without measurement, because if you're starting to go out and measure, that means you're moving to a more complex study. This is a pre-existing score you have access to. No additional testing is required. But you do need that mean and standard deviation. Now, how we calculate a z-test? We take the mean of your sample minus the actual population mean, in this case represented by mu. And the bottom of the equation is a small little sub-equation. We take the standard deviation, sigma, again of our population, and we divide it by the square root of our sample, n. Once we have those 2 values, we basically just run the math. So how many standard deviation units is the sample mean from the population mean? That's what this is calculating. So if I calculated a z-score of 2.22, 2.22 is above 0.196, either positive or negative, which means in this case, I've obtained the requirement to say this value is significantly different than the mean, either positive or negative. Now notice this is a two-tailed test. If you do have a reason to expect, I expect this group to be better or worse, you can have a directional hypothesis. And in that case, your obtained z-test simply needs to be plus or minus, depending on the direction of your hypothesis, 1.645. So again, the components of everything we're going to do statistically are here. We are using a mathematical equation, though a simple one, to get an obtained test score. We're now going to compare that obtained test score to an actual criteria for alpha. In this case, though, that criteria never changes. It's always based on our z-score table, and it's always based on the idea of how many standard deviation units does your group need to differ from the group that you're comparing it to. And in this case, for you to be 5% certain in a directional hypothesis, the obtained score needs to be plus or minus above 1.645. If you have a non-directional hypothesis, that obtained test score needs to be above a plus or minus 1.960, and you can now say if your value, in this case 2.22, is higher, you have statistical significance of a p less than 0.05. The assumptions of the z-test. All tests have assumptions, some of them statistical, some of them methodological. So some of these are just what you have to run that. You have to have the known population mean and the known standard deviation of that population. You have to have access to both. You have to have a sample mean using either interval or ratio data. You have to have independent observations. What that means is it's kind of it's a blurry methodological concept, but independent observations means that your sample was not influenced by the group you're comparing it to. Generally speaking, most experimental methods automatically have independent observations, but you do want to look out for this as a potential. For here's an example of violating independent observations. You have two classes, one right after the other. You decide you're going to do an intervention in class 1, but not an intervention in class 2. So the 8 a.m. class gets the intervention, the 9 a.m. class does not. You do the intervention in the first class with a pre-test and a post-test. So they come in at 8, you give them a pre-test, you do the intervention, at the end of the class you give them the post-test. You're going to do the same thing in the next group to make a comparison, your 9 a.m. class. However, there's that 10 minutes between the class. And as you're watching everyone from your 8 a.m. class leave, they start talking to the people coming in for your 9 a.m. class, telling them about the awesome intervention you just did. They've just influenced the scores of your control group. That would be a violation of independent observation. The distribution of your actual sample has to be normal, so you need to test for skewness and kurtosis. And finally, you have to have a sample size of over 30, 31 plus. So if you have all these assumptions, you don't need to do a t-test. You can use a z-test, and it is the appropriate statistic to use. However, notice there's some situations where we might not be able to use a z-test. For one, we might not have the standard deviation of a known population. It's a lot of times you'll find in publications people telling you what the average of a score is. It's not so common, especially in non-scientific literature, to find a standard deviation, so that might be missing. Also, you may actually have less than 30 people in your sample. In both of those cases, you would need another test for a single sample research, and that's what we're going to talk about next, the t-test for single samples.